Hi, I'm Junlin from Data 6-in-1 CSIRO and Australian National University. We present a new image-to-image translation model based on contrastive learning. Image-to-image translation aims to learn the mapping from one domain to another. It has multiple applications like style transfer, super resolution, and image restoration, including dehazing and derailing. Some examples are shown here. This is an example of from horse to zebra. This is from cat to dog. This is from semantic map to realistic photo. This is from low resolution to high resolution. And the last one is raining image to rain-free image. What is unpaired image-to-image translation or unsupervised image-to-image translation? Let's say we want to train a model that translates a cat to a dog. We can collect a dataset of cats and a dataset of dogs, but it's impossible to employ supervised training because we cannot collect a pair of cat and dog with same pose, background, and composition. Thus, we learn the mapping from cat to dog in an unsupervised manner, and we want to the model looks like this. Current methods for unsupervised image-to-image translation are mainly based on two assumptions: the cycle consistency assumption and shared network space assumption. They usually have some limitations and drawbacks. For example, the cycle consistency assumption forces the input image and its reconstruction image to be identical, which is sometimes too strict and not good at performing geometry changes. Recently, contrastive learning has become more and more popular in computer vision. CART first employs contrastive learning to maximize the mutual information between input and output patches. Our work aims to further explore how to make use of contrastive learning more efficiently. Here is a demo of CART. The goal of NCE laws is that given a red patch in the output image as query, we need to find its yellow positive patch with same location other than rest of the blue negative patches. CART uses one projection head and one encoder, where the encoder is the first half of the generator, to extract patch information from input image as well as the output image. Our question is, does one encoder and one projection head be able to capture the variability in two distinct domains, especially when two domains have a large gap? How about making a small change here? That is, assign a unique encoder and projection head for different domains. To do so, we need to add one more generator from domain Y back to domain X. Thus, for different domains, we can assign its unique encoder and projection head. And we also need to add the discriminators for both X and Y domains. We name our method DCLGAN, where DCL is short for dual contrastive learning. And images inside one domain should share a similar style, regardless of whether it's generated or real. Thus, we add a similarity loss to encourage images with one domain to have some similarities in deep features. We name this one as SAMDCL, where SAM is short for similarity. CART employs 5 levels of layers inside the encoder. That is, 5 different levels of patch sizes. However, the first layer CART also includes the RGB pixel, which is the 1 multiply 1 patch. In this example, the 1 multiply 1 patch of the cat is around its right ear, but after translation, this part actually becomes the background. So we think RGB pixel does not beneficial to the learning process, and we remove it. To compare our methods with other state-of-the-art methods, we use 6 different datasets and they are with 9 different translation directions. For metrics, we mainly use the FID score. For cityscape, we also use the IOU, pixel accuracy, and class accuracy. We first compare our method to 8 other state-of-the-art methods on 3 different tasks. DCLGAN achieves the best result in effective score in all 3 tasks with acceptable running time. SAM-DCL also showed good results with 2 tasks on the 2nd place. Here, let's look at some video examples. It's clear that DCLGAN outperforms other methods in both quantitative metrics and the qualitative results. DCLGAN is also good at performing geometry changes. This is shown in the translation between cat and dog, where DCLGAN is trying to change the shape of ear and mouth to perform geometry changes. We select the best 4 methods for the last comparison on 3 tasks and conduct one more experiment. DCLGAN still consistently outperforms other methods overall. Also, DCLGAN trained with 200 epochs only show the best result in dog-to-cat translation, better than cat trained with 400 epochs. More video examples are shown here. DCLGAN tends to perform a more natural translation. DCLGAN has less constraint than count and cycle GAN. Thus, it's good at performing geometry changes to match the distributions. Here are some examples. This property can be good if geometry changes are required, but it's more a personal taste. Since DCLGAN outperforms all state-of-the-art unsupervised methods, how about supervised methods? Can DCLGAN also bridge the gap between supervised methods and unsupervised methods, just as contrastive learning in the field of representation learning? To explore this, we conduct one more experiment on the cityscape dataset with 3 supervised methods. Surprisingly, we find that DCLGAN is on par with those supervised methods. This suggests that the gap is closing. For ablation study, we explore 5 different variants. Variant 1, 3, 5 are our main difference between cards. We show that each component of DCLGAN is useful. For variant 2, we add external negatives in a semi-clear style. It does show a better result than vanilla DCLGAN in hosted zebra. However, we find that objects in the generated images tend to be merged together for this variant. Here are the video examples for all ablations. We can see that variant 2, which uses the external negatives, tends to merge objects together in a part labeled with red circle. Also, the result of DCLGAN is more visually realistic than the rest of them. Many thanks. This is all. Please feel free for any questions.